Good evening, everybody out there in television land, mums and dads, boys and girls and bald-headed babies. My name is Michael Wilson, and I'm your host tonight for the June 2022 meeting of the Ottawa Centre of the Royal Astronomical Society of Canada. And welcome to any and all visitors joining us from other RASC centres or future historians discovering this in an archive somewhere. Next slide, please, Chris. Usual provisos that we are recording this and it will be available on our fabulously provisioned website at ottawa.rasc.ca in the immediate future. If you wish to raise a question or make a comment to any of the speakers, please use the Q&A, not the comments. The comments are not monitored. Chat box comments can be seen by everyone, so be discreet. Watch out for those nasty pirate URLs, which we haven't seen any of anyway, but just beware. And note that the raise your hand facility is disabled. Next, please. So after this little introduction and rant, I'll also be covering Ottawa skies for June, given that Dave is away with the Boy Scouts. We'll then have our first guest speaker, Nathalie Ouellette, on the dark matter and galaxy evolution, to which I'm looking forward greatly. Bob Olson will then walk us through the Cassinis family and their work in astronomy and geodesy and what influence that had on the development of France as a country. Normal 5-minute break and AstroTrivia, although it's not normal this month. In fact, there's a couple of weird things we're doing this month, and the break is one of them. Andrea will give her introduction to Milky Way astrophotography using a simple tripod and SLR camera and stuff. Good entry-level sort of presentation. We've got lots of observation reports, and I may have to sort of squeeze those in order to keep us to time. I'll then be covering Oscar's observing challenges for the next month, and we'll come through to the announcements, including the fact that tomorrow, whether participating and cooperating, there will be a star party at the Carp / Diefenbunker parking lot, but we'll have more about that towards the end. Next one, please, Chris. 3 new members this month, so welcome to Mark, Yolanda and Jeffrey. Hope you're here, and I hope you're considering what particular presentation you might like to make to introduce yourself to the other members. 28 members so far this year. I don't know how that tracks against statistics. Seems a little bit low to me, Chris, but what the heck. Next one, please. Okay, so first unusual thing for this meeting. We have an offer from Calvin Klatt, who unfortunately isn't yet able to join the meeting, but he's offering to do what he described as a 3D walk and guided tour around the Dominion Observatory buildings. Apparently he prepared this for the Open Doors program 3-4 years ago and is willing to rerun it for us. His proposal is that we pick a Saturday evening during June and July when, heck, there's not much dark sky anyway. It'll be an opportunity to learn history and Canada's role in the development of standard time system. You'll get the chance to straddle Canada's prime meridian, feed in different hemispheres and all that. We'll see the transit house. Possibly, if we get organized, we could have a barbecue and a social event as well. If you're interested in Calvin's proposal, please send your note of your interest, including your preferred date, to me as meeting chair at ottawa.rasc.ca. I don't know if Calvin's got a minimum number in mind, but hey, obviously the more the merrier. Next one, Chris. Our usual conversation as to why the cost of membership with RASC is worth it. Sorry, it's just my cat. Next one. Member benefits include, when we have physical access back at Chasm, to the Telescope Loan Library, to the book library. In the meanwhile, you do have access as members to the Fred Lossing Observatory out near Almont, and your ability to register and participate in the various observer programs that the RASC makes available to all members. Next one. As far as information assets, apart from our fabulously provisioned website, there's the Sky News, bi-monthly popular news magazine on astronomy with a Canadian bent. There's a more formal journal of the Royal Astronomical Society, a bit more academic in nature. There will be the next Observer's Handbook. Well, you'll get this year's, but it's sort of reaching its use-by date. But there will be another handbook for 2023, world famous publication from RASC. And in the meanwhile, there's our own Ottawa monthly newsletter, Astronotes. So those are the bribes and goodies. As some of you, most of you have heard me say before, I think the biggest bribe is the opportunity to meet up and engage with people, both the members of the centre as well as our guest and invited speakers. That to me is the ultimate benefit. So with that, Chris, I will now run through the Ottawa skies, and I'll do my best Dave Chisholm voice for the purpose. No, I won't. Okay, so phases of the moon for this month. Full moon is on the 14th. I have no idea what the folkloric names for this moon are, so we'll just call it the Dave wasn't here moon. Next one. As everyone I suspect already knows, there's this rare alignment conjunction, well, not conjunction, but a rare gathering of basically 9 major bodies on the same side of the solar system, and it's visible to us in the pre-dawn sky in the morning. So you've got all the major planets, you've got a major asteroid, Vesta, and the moon comes and goes. So it's a pretty opportune time to actually get up at around 4:30 in the morning and go out and see this. As you can probably work out, that makes the rest of the sky news for this month rather boring. We can move on.
You think, Dave, that we'll have a few observations to show next month of this event?
One would hope. So, sunrise, sunset, we're approaching the summer solstice, as you call it up here. So days are still getting longer, but decreasingly rapidly. Next. Okay, Mercury, believe it or not, is visible in the morning sky, pre-sunrise. More specifically, June 16th, it will be at its greatest western elongation, i.e. as far from the sun as it's going to be in this season. And so your best opportunity for picking up Mercury if you haven't done so before. Next one. Venus is also visible before sunrise. Mars is also visible before sunrise. Jupiter is also visible before sunrise, and so on, and so on, and so on. Visible before sunrise. Uranus and Neptune, guess what? Show us, Chris. Visible before sunrise. There we go. Our bit of humor from Dave for this month. I think it's a bit sexist, but oh well.
But in summary, Mick and Dave, we thought astronomy was a hobby that people normally do in the evenings. We've all got to switch gears and do it in the early mornings. There are virtually no planets available in the evenings, including for our star party, but mornings are fantastic.
Mornings, well, we just have a star party in the morning. How's that? All righty. So with no further ado, Chris, I think I would like at this stage, oh, hang on, yes, important thing. We have a number of open positions here in the Ottawa Centre. We need a public outreach coordinator, someone who's willing to interface with the press and other aspects of the media, as well as presentations to public groups and so on. Could be a fun job for any of the teachers that are out there in the audience in particular. The hospitality posts, yep, they will need to be filled when we get back to the chasm, tea, coffee and snacks. Not an immediate urgency, but if you'd be interested, then putting your hat into the ring, even now, would be appreciated. Finally, I am the current sole national representative to RASC National, and it would be really great to have a partner / backup for that job. It's a 2-hour meeting quarterly. It's not a huge ask, and you get to learn lots about how RASC actually operates as an entity, a legal entity. So any interest in those, again, please send expressions of interest to me as meeting chair at ottawa.rasc.ca. Next one. Okay, finally, now we get to the chunky part. So I'd like to reintroduce our invited speaker, Nathalie Ouellette. Some of you will remember she presented back in December 2019 on the projected project aspirations for the Webb Telescope, JWST. I suspect she's going to come back and update us a bit on that tonight. Her main topic is about dark matter and galaxy evolution, as she refers to it as nature versus nurture. Her background is in astrophysics. As you can tell, she's an avid science communicator, researches in galactic and cluster formation. She coordinates the Institute for Research on Exoplanets and is the outreach scientist for the JWST in collaboration with the Canadian Space Agency. So she takes science seriously, but not herself so much. So we'll see what she's got for us tonight. So thank you, Nathalie. Over to you.
Great. Thanks so much for the invitation. I'm happy to answer any questions people have about Webb tonight, but I actually am focusing on something else, just because I know that there's been a lot of saturation around Webb, and once the first images will be released, I'm sure you'll have lots of interest and people speaking about that as well. So I'll just go ahead and share my screen. If someone can confirm that they can see that.
Yeah, no problem.
Perfect. All right. Yeah, so I'll be talking a little bit more about my research interest, my research field. I still try to do research whenever I have the chance. I'm actually just finalizing the submission of a paper. So when I have the time, I continue to do research, although I have less and less time to do so. And as Mick mentioned, I am particularly interested in galaxies that are in cluster environments. So I'll talk a little bit about that, why I find those particularly interesting, why they're very important to understand galaxy evolution. But as was mentioned, I actually work at a place called the Institute for Research on Exoplanets. I've been there since 2018. It is mostly centered at the University of Montreal, but with members at other institutions in Quebec. And it's been very, very interesting. I've been learning a lot. It's been alienating at times because I work with roughly 70 other people who don't care about galaxies at all. So I'm always sort of like in my corner doing my own research, but I get to learn lots about exoplanets, which was not my field of study in my graduate studies, and it remains not my field of study. But it's really given me the chance to learn, and I think that it's always good for them to have an outsider point of view when they're doing their research as well. But so I'm here in this field of other people, the lone extragalactic person, which means that basically the entire time that I've been there, I've been very much feeling like an outsider, like a fraud, like an imposter. I counted, and it's been about 1,368 days. People still seem to accept me, even though I'm a galaxy lady rather than an exoplanet person. So I'm surrounded by a really good group. So when we're thinking about galaxy evolution, galaxy formation, you need to think about structure formation in general. And so we're looking at different scales where things are forming. So if you're looking at the entire universe, the largest structure that you can form is called large scale structure, not particularly interesting. So large scale structure, when we simulate it, it's all these filaments, and within these filaments, there are areas where it's very dense, where you have lots of galaxy clusters forming. And outside of these filaments, you have what we call voids. So it looks like a big spider web. The web itself is where matter is gathering, both dark matter and normal or baryonic matter. And then you have these voids. So you have small oscillations in the density of the universe that ended up collapsing into this sort of web form. And so we can shape this in simulations fairly well, partially because at this scale, dark matter dominates everything. And even though we do not know what dark matter is, we understand how dark matter acts and reacts fairly well, because at those scales, the only thing that matters is gravity, essentially. And for astrophysics, gravity is pretty much the fundamental force that we understand the best. When you're looking at electromagnetism, when you're looking at what we call gastrophysics, or feedback due to the creation of stars and gas and all that kind of stuff, those are the details that we have a harder time with, actually. But when we're comparing what we simulate for large scale structure and what we see when we're looking at the actual universe, so this is real data that is placing structure and galaxies on a map, essentially. You can see that it corresponds pretty well. So large scale structure is pretty easy to model because dark matter and gravity are the most important things at those scales. If you go to a smaller scale, if you're looking at a specific bright spot in the filaments, you go down to a galaxy cluster scale. So what's inside a galaxy cluster? So here again, the great dominating amount of matter is in dark matter. About 90% of what we find in here is dark matter. And then the next step, the next biggest, most important component of galaxy clusters isn't even galaxies yet. It's all the very, very hot gas that we find between galaxies. This is called intra-cluster medium gas. So it's between the galaxies and it's heated quite hot. It glows in the X-ray, but this is not what galaxies are made of yet. So galaxies only account for about 1% of what is going on inside of these galaxy clusters. And if you're familiar with parsecs, the size of a galaxy cluster is typically on the order of 1 to 10 megaparsecs. And these can include hundreds or even thousands of galaxy members on the inside. But again, because dark matter is the dominant type of matter in these at these scales, it's harder to model, but it's still relatively easy. What we're finding in our computer models and what we see in nature match up pretty well. Now, we're going to the really small bits that we find super interesting, and I know lots of you must do great astrophotography of galaxies. Things start to get a little bit more complicated because even though dark matter is still important, normal matter starts being very relevant here, and the interactions involved with normal matter start being complicated. So this is what a galaxy is typically. You have different components. At the center, you have the nucleus, and the great majority of galaxies have a supermassive black hole at the nucleus. This is what we call the sombrero galaxy. It's a lenticular galaxy, sort of halfway between a spiral and elliptical. There's a bulge at the center, a sphere of stars that has more dense, higher concentration, and you have a disk in this case. So a flattened out disk where stars are rotating around the center. But all of this is the visible part of the galaxy. This is embedded inside of a dark matter halo. And if I tried to really show to scale how big the dark matter halo is, it would fill up your entire screen. Essentially, the dark matter halo extends up to 10 times the radius of the luminous part of a galaxy. So it's much, much bigger. But embedded at the center of the galaxy, you have the luminous part, and the luminous part starts being very, very important. So you have two main types of galaxies: spiral galaxies, which astronomers call late type galaxies, and elliptical galaxies, which astronomers call early type galaxies. It's a bit of a misnomer, but unfortunately, astronomers have quite a few misnomers, and our magnitude scale is upside down, as you know. So we're sort of like stuck with these relics of how people used to do astronomy way back when. So when you're looking at a galaxy, there are lots of complicated things going on inside. So we try to look at the different relationships between these different parameters: the brightness, the color, the stellar populations, the mass, all these things. We try to equate these different parameters together and try to find relations that help us explain how these galaxies form and evolve. And so these are called scaling relations. This is the main way that I study galaxies. We're also looking at the angular momentum content. So angular momentum we know needs to be conserved. So it's something that carries through the entire evolution of the galaxy. So by tracking that angular momentum, how it changes, where it's displaced in a galaxy, that tells us a lot about the evolution. There are a lot of problems as well when we're looking at galaxy scales. Some of you might have heard of something called the missing satellite problem, wherein it seems like when we are doing simulations in a computer, we should be finding nearly 10 times as many satellites as we do in nature. Now, is this because our equations are wrong, our simulations are wrong, or is it because there are lots and lots of small galaxies, but our telescopes and our instruments aren't sensitive enough to pick them up? So here we have this issue where maybe our instrumentation needs to catch up to our theory, or maybe our theory needs to be adjusted to match up with nature. There are other problems. There's one called too big to fail, where we're finding that galaxies that should be igniting star formation are not doing so. Lots of different things related to the shape of a galaxy near its center. This is called the cuspy versus chord halo problem. So essentially, galaxies are the hardest to model, and we still have a lot of work to do. But don't despair. We've done a lot of improvements over time, and a lot of that has been due to two things. So number one, our resolution for our computer simulations has greatly improved, which means that you can nearly have one particle or one pixel for every star that's inside of a galaxy. We're not quite there yet, but it means that the resolution when we're running these simulations of galaxies is higher, so they are closer to how it's really happening in nature. And as our resolution has improved, we're actually seeing a better match with what we see in nature. So as resolution will improve, as computers will get faster and faster and more powerful, we're hoping that the bridge, the gap between theory and what we see in nature observations will start closing a little bit. And then the other thing is that our understanding and modeling of the complicated kinds of physics, the gas physics, the feedback caused by a supermassive black hole, or what happens when a star explodes and it blows off a bunch of wind into its surroundings and injects energy in the galaxy. We are understanding that better, and we can incorporate it into our models better. So all of this, we need to improve our models, but we also need to improve how we are observing galaxies. So that is where I sort of come in, and the people that I work with come in. We are observational astronomers. We're not dealing with the theory and the computers, but we work very closely with the people who do. And one of the big questions that observationalists are trying to answer is, what is the biggest driver in galaxy evolution? Is it intrinsic things inside the galaxy, their nature, or is it their environment? So there is a similar concept in anthropology called nature versus nurture. It treats how humans evolve over time. How much do their genes affect who you will become versus how much does your environment affect who you become? And so just like with anthropology, we think that it's a mixture of those two things. You are not solely defined by your genes. You're not solely defined by your environment. It's a little mix of both, and maybe some like supplemental, like otherworldly thing that just makes you who you are that we haven't been able to define yet. So in the case of galaxies, what is their nature? So these are internal things that they're born with to some degree. So this includes their mass, how much mass they have, and we can track this through their luminosity. What kind of stars do they have? And this is something that we can track through the color of the galaxies. So galaxies that are very blue, very whitish, very purple, they will have a lot more younger stars. A galaxy that's more red will have older stars, older, colder stars. Internal dynamics, we can see where the mass is positioned inside the galaxy, how much gas, how much dust is inside that galaxy, and magnetic field as well. We're looking at how the stars are moving around. So these are all things that are inside the galaxy itself, and those do affect galaxy evolution quite a bit. But I am very interested in galaxies that are in clusters specifically. So I always like to liken galaxies. I tend to anthropomorphize a lot of things in general, and I do that with my galaxies as well. I sort of see them as animals who live in herds. And I've chosen to study galaxies that live in very, very large herds. So my particular herd is the Virgo cluster. Same thing here as most galaxies. These galaxies have grown and evolved within a group with hundreds or thousands of other members. And just like humans, these galaxies are affected by not only their environment, but the other galaxies around them. So there's almost like a social structure within these clusters. And you can see a bit closer in within that cluster, you'll have smaller groups and you can start seeing a lot of interaction. You can see these two galaxies specifically that are interacting with each other in that picture. So what is affecting galaxy evolution in terms of nurture, in terms of environmental effects? So as I mentioned, you can be interacting with your environment. So even when you're not talking about other galaxies, the environment, the cluster environment can affect galaxy evolution. So if you'll remember, I talked about galaxy clusters and how about 10% of galaxy cluster mass isn't found in the galaxy, it's found in the gas, it's between the galaxies. So as a galaxy moves around within the cluster, it interacts with that gas. So this is a phenomenon called ram pressure stripping. And this is a galaxy here that's sort of free falling downwards into the cluster. And sort of like if you imagine someone jumping off a plane, you'll have air resistance pushing their bodies and their limbs up. This skydiving galaxy basically has its disk that's being deformed by the interaction with the gas. And sometimes this will actually tear gas out of the galaxy and stop star formation within that galaxy. So you're not even considering other galaxies in this point. But of course, there are other galaxies as well, depending especially where you are in the cluster, you'll have the high concentration or density of galaxies. And these galaxies can harass each other. You have what we call tidal interactions, where through their gravity, one galaxy that's smaller will be sort of torn apart or deformed, or they can literally just collide together. And so here you'll have two galaxies that will form one. Sometimes one galaxy is much larger than the other, and the smaller one will be cannibalized. So being cannibalized certainly affects how you evolve. Luckily, we can see evidence of this going on even after the collision or the cannibalism event has occurred, because it often leaves traces in how the stars are moving around, what we call stellar streams. So they sort of track how a galaxy has fallen into another galaxy. So we can study all those different things. So this is a simulation of two galaxies that are interacting with each other, but at different stages of the collision, we can freeze frame and find basically an analogous real picture, real two galaxies that are interacting in this manner. So this is sort of one of the challenges of studying the evolution of galaxies. These collisions happen over the course of hundreds of millions of years. Galaxies evolve over billions of years, and we unfortunately do not live on those time scales. So what we need to do is either run a simulation and run it fast forward in a computer so we can sort of see how they evolve over time, or we need to collect data from thousands, tens of thousands, hundreds of thousands and millions of galaxies at different stages of their evolution. So you do this by looking at galaxy surveys, essentially. So as instruments have improved, we've been able to develop these surveys that have been able to collect pictures and spectra of hundreds to now hundreds of thousands of galaxies for a single survey, essentially. So these are a few examples. SDSS, or the Sloan Digital Skies Survey, has been really effective, and all the data is publicly available online. These other ones you see here, these are what we call IFU surveys, or integral field units. They can take spectra, but they can take basically a spectra over 2 dimensions. So there's like a lot of spatial resolution in the images you take. And the survey that I run is called Shiver. So it's a Canadian-led survey. So we were thinking of winter when we named it, essentially. And it uses what we call long slit spectroscopy. So Shiver is very interested specifically in the Virgo cluster, because Virgo is a super, super well-suited cosmic laboratory to study galaxy evolution, because number one, it is extremely rich. There are over 4,000 galaxy members inside of this cosmic lab. In comparison, there's about 100 galaxies in our local group. Number two, it's very well studied over lots of different types of light. So if you are focusing on one kind of data and you need supplemental data in different kinds of light, in photometry instead of spectroscopy. Lots of people are working on this together. So it's very effective. We can share data. And number three, it's also a relatively young cluster, which means that it has all types of galaxies. So typically, as a cluster gets older, its environment is processing spiral galaxies and turning them into elliptical galaxies. So if you look at a cluster that is too old, you will find an overabundance of red and dead elliptical galaxies, which aren't really forming stars anymore. But because Virgo is young and full of action, it still has lots of spiral galaxies inside. So you have a good range of different types of galaxies to study, how they're interacting and how they're evolving over time. So the Shiver survey has lots of data on it out already. We have both photometry or images. So the brightness lets us know about the stellar mass, the stellar types, the stellar populations, the shape, whether they have disks, whether they have bulges, if they are barred disks, lots of different things in the morphology. And the spectroscopy, which is what I specialize in, tells us about the movement of the stars. It tells us about how much dark matter is inside of these galaxies, total matter. And it also lets us try to figure out how dark matter and normal matter interacts within these galaxies. If you're very interested, a lot of our data is available online, and these slides can be made available afterwards. So all of our data is available there if you want to start looking into what we do. But essentially, the thing that we and I am very interested in looking at all this data is those scaling relations that I mentioned early on. So as we are basically making these figures where we have one parameter, like say mass, and another parameter, say color or luminosity or whatever, we're trying to figure out how these different parameters relate to each other. So these are these scaling relations. And distinct slopes and trends within these scaling relations are basically telling us the different processes, the physical processes that are happening within the environment of the cluster, within the galaxies themselves, and how they're assembling together. So this is some example here. This is one scaling relation that equates stellar mass and what we call effective radius, or the size of a galaxy. And we can actually sort of trace these evolutionary lines on these plots where we see that spiral galaxies are turning into elliptical galaxies as all of their gas is spent and they can no longer form stars, or as they're colliding together and getting bigger. So these are all the different types of things that we can do with these scaling relations. And as we continue these types of data, these types of observation programs, we are very excited about having data from bigger telescopes that can look at smaller galaxies. This is a big issue that I'm having right now. Essentially, the majority of galaxies within these clusters are what we call dwarf galaxies, and they are a pain to observe because they're not very bright. Their surface brightness is quite low. So you basically have to stare at it for 4 hours with the largest telescope that exists in the world right now to get a little bit of information on them. And ideally, we want to be observing hundreds or thousands of these galaxies. And I know I'm maybe a good scientist and a charming scientist, but no one's going to give me millions of hours on a telescope. So if the telescope is bigger, then it is simpler and more effective for me to look at these dwarf galaxies. And eventually, we'd love to take these studies and look at different clusters as well. So the Coma cluster, the Fornax cluster, they are at different stages of their evolution. So it gives us even more data points to figure out galaxy evolution in these different environments. So that was like a really fast overview of what I do for galaxy evolution. I'll leave it there and I'm happy to take any questions.
Sorry about that. I was dealing with a question from Chris. Well, okay, beauty. Thank you. Excellent presentation. I think instead of herd galaxies, having lived in Africa for as long as I did, you need to start calling them wildebeest galaxies, living in vast herds across the plains of the Serengeti.
I think of elephants for whatever reason. I always use elephants as an example, but wildebeest is a good one too.
It is, numerically. As usual, we've got a couple of questions coming up. I always like to start the Q&A sessions by portraying and displaying my ignorance On about your seventh slide there, you had the full cosmological scale portrayal of the web. And there was a scale bar with the units, looks like megaparsecs over H. And I'm just asking, what's H?
Yeah, so let me just pop that back up. H here is the Hubble constant.
That's
so in these particular, simulations, we typically have like this cube that simulates the universe, and we have all this like structure forming inside. But we know that we are not in a universe that is like statically shaped. It is an expanding universe, but we don't want to be running our simulation in a cube that is expanding forever. So really what we're doing is we're keeping the cube the same size, but the scale inside the cube is changing as the universe is expanding. So it's like a little trick that we use to run those simulations while still respecting the fact that the universe is expanding.
Okay, that makes sense. It's a sort of a four-dimensional snapshot as far as the scale factor goes, I guess. Okay, so to the questions that have come in online, first of all, congratulations from Simon Hanmer saying your presentation was brilliant. Dennis O'Farrell asks, how much do you know about how much and where dark matter is? I guess density distributions.
Yeah, so this is something that I did a lot in my PhD and my master's thesis, actually. So you can look at a galaxy and you can look at how fast the stars are spinning around a galaxy. So if you're looking especially at a spiral galaxy, all the stars are spinning or rotating around the center of the galaxy, much in the same way that planets are orbiting the sun within our own solar system. So when you do that, you can measure the speed of those stars and you can estimate how much total gravitational mass is within the orbit of those stars. But the issue is, and we've known this for a few decades now, if you count up all the bright stuff, all the normal matter that is shining light, so the stars themselves, the gas, the dust, etc., you add it all up, you fall very, very short of the total gravitational mass that you measured. So the difference between those two is your dark matter. And if you have spatial resolution in your spectroscopy and you're doing that in different spots, you can actually track where the dark matter is located. There are different ways you can do that too. There's like gravitational lensing, where if you have a big cluster between you and a far away galaxy or object, that galaxy cluster will warp space-time and change sort of the image of the galaxy that's very far away. And depending on how that far away galaxy's image is deformed, you can actually patch and track where the dark matter in the galaxy cluster is that causes that gravitational lens, that deformation. So it's possible to sort of track it like that. But yeah, it's mainly by looking at the motion of stars and realizing that it's much greater than all the luminous mass that you're putting together.
Judy, that seems clear. Our next question is from Chuck O'Dale. He states that it seems that spiral galaxies are the closest to us. This would infer that it is the oldest class of galaxies. Is this possible?
So we happen to be in a spiral galaxy, and our big sister Andromeda is also a spiral galaxy. But the majority of galaxies within our local group are either ellipticals or what we call irregular galaxies. So irregular galaxies are smaller. They never really got their act together to start having a nice, really spiral structure or anything like that. So really the overwhelming majority of galaxies are irregulars. But we do know that spiral galaxies will evolve into elliptical galaxies. And one way you can look at that is by looking at their color, which hints at the type of stars that they have. So because spiral galaxies are overwhelmingly dominated by the brightness and the light of very young stars, we know that those galaxies are younger as well. Elliptical galaxies will be redder, so they will have older populations of stars. Basically, all their young blue bright stars will have died out because they're older galaxies essentially. So other than that, I'm not sure what Chuck means by spiral galaxies are the closest to us. I think spiral galaxies get more attention than elliptical galaxies, and they can sometimes be a little bit easier to observe as well, just because a lot of the light is concentrated in the disk. Elliptical galaxies can be a little bit harder to study, but no, elliptical galaxies are definitely older than spirals.
Thank you. Next one, we've got 3 more in the list, and I think I'll close it there. So these 3. Joe Holmes, great presentation. I've heard somewhere that Andromeda is actually much bigger than what we can normally see. Is this true? And how big would it appear if all of it could be seen with the naked eye?
Yeah, so Andromeda is embedded in a dark matter halo, the same way that all my partner's trying to sneak behind me. You can go. You see, you can't even see him in the background. All right, perfect.
Dark matter.
The joys of working from home. Yeah, I know, he's dark matter in my universe. Yeah, Andromeda is embedded inside of a dark matter halo. And so similar to all galaxies, the dark matter halo is probably on the order of 5 times larger than Andromeda's luminous part. And so if I remember correctly, the footprint of Andromeda is something like twice that of the full moon. It's surprisingly large when you can actually see all the luminous matter. And that's like with a really good telescope though, like, and not a lot of light pollution. So it'd be on the order of 5 times larger than that in the sky if we could see dark matter. But that's the thing with dark matter. It doesn't shine, so we can't actually see it.
Next one, Brian Carroll. As opposed to simulations, do your observations require computers? And if so, are your observations limited by computing power?
So I do use computers because I do all of my data reduction and my data analysis on a computer. And I do sometimes need to do things like running simulations to match up against my observations. But I do not need clusters of supercomputers the way the theorists do. So it's really not on the same level at all. But all astronomers basically have to use computers now.
Great. Last one from Simon Hanmer. Where are things at regarding the identity of dark matter?
So that's a great question. So this is sort of in the realm of astroparticle physics. As astronomers, we try to gather lots and lots of evidence to how dark matter acts, to try to put constraints on the search for the identity, the nature of dark matter particles. Astroparticle physicists instead build detectors that they put all over the globe underneath the crust, well, not the crust, but underneath the earth, inside of mountains, to try to detect these dark matter particles exactly. So there have been some signals that were like almost, is that dark matter? I'm not sure. And then they couldn't be verified conclusively. And so we don't have any conclusive evidence that we've been able to find dark matter yet. But there are better and larger dark matter detectors being built right now all over the globe. So I think we're getting closer. And essentially, these different dark matter detectors are probing different sizes of particles, different energies, different cross sections. And if they look very hard in a specific region of that like search area and they don't find anything there, you're sort of at least cutting away different possibilities of what dark matter could be. So we're sort of trying to pin down a region where dark matter could be in that sort of like search space. So nothing conclusive yet, but people are definitely hard at work trying to figure it out.
Okay, and I'll sneak in one last question because it is from one of our panelists, Chris, and he's asking, has the quality and resolution of amateur images of galaxies reached a point where they're useful to researchers?
That's a good question. I'm not super familiar with the resolution that amateur astrophotographers have for their images. I know for dwarf galaxies, certainly even the professional telescopes are having a really hard time trying to study that. I know that there are really great citizen science programs related to classifying galaxy morphologies and everything. But when we're looking at galaxies, we need to use essentially huge telescopes that have resolution from mirrors that are like 10 meters wide. So it's sort of hard to fight against that or try to contribute to that. I can say, however, that certain types of instruments that are really more akin to normal cameras have been unexpected champions in terms of looking at different types of galaxies. So there's a project called Dragonfly that is led by Princeton and the University of Toronto. And rather than using a telescope, they use these photo lens arrays. That's why it's called Dragonfly. It's sort of like a dragonfly eye. And they are very good because they don't have a lot of internal reflections inside. So they are excellent at looking at very, very low surface brightness features of galaxies. So that's like really more of an astrophotography tool that's been used to do professional astronomy. It was sort of like an unexpected thing. So I think, yeah, there's like potential things to do in that realm.
Beauty. And with that, I will say, thank you once again. I warn you that somewhere after the JWST images start rolling in, I'll probably come back and harass you again.
That's fine.
Big round of applause. Thank you, and until next time. Cheers.
Thank you.
Okay, so Chris, back to you. And now our second presentation. Many of you already know Bob Olson, but for our newer members, he's an avid and experienced astrophotographer and a frequent and prolific contributor to our monthly observations. A lot of these are generated from his own specialized imaging telescope that he has constructed and informed us about over the years. As a true Renaissance man, he blends these sort of mechanistic pursuits with an interest in the history of astronomy. He also now has a recent history in alligators. So with that, I'll hand over to Bob, and he's run through on the Cassini family, a very interesting group, and the mapping of France and where that led to the modern world. So thanks, Bob.
Chris, are you running the slides?
Chris, are you running? Yes.
Thank you, Chris. You'll notice two names in the title. The first is his Italian birth name, and the second in brackets is the name he adopted when he moved to France in 1668, when he was 43 years old. His name change can be a source of some confusion. He lived to be 87, and those 87 years were very interesting. Next. When Mick approached me about this talk, one of his first questions was, what do you know about Cassini? I responded that I think he invented Saturn. Next slide. I also mentioned that I think he owned a spacecraft company and that may be related to Elon Musk. Number 4. Next slide. Mick's response to this was, I have a book I need you to read. You might ask, what on earth do maps have to do with a famous astronomer? We'll get to that later. Next. Cassini was born in Parinaldo, Italy. Interestingly, when I looked for this town on Google Maps, it highlights the Cassini Museum. One of the reviewers states that this museum will allow you to discover who this brilliant astronomer was. Cassini was raised there by his uncle, his mother's brother. Next. This is what the town looks like now. Next. He studied at the Jesuit college at Genoa under Caselli. Next. Next slide, Chris, please.
I did move to the next slide. It added an arrow.
It's not showing up on my, oh, maybe, I'm sorry. Cassini was, he studied at the Jesuit college at Genoa under Caselli. He then studied at the Abbey of San Fructuoso. It was astrology that interested him in astronomy. He soon became an expert astrologer, which I find hilarious, as he had no personal belief in it. He felt that astrology had no ability to make predictions of the future, but it was astrology that led to his first professional position. Next slide. This is the Abbey, which seems more elegant than the educational institution where I taught. Next slide. In 1644, the Marquis Cornelio Malvasia offered Cassini a position at the Panzano Observatory, which he was constructing at that time. The Marquis was a senator from Bologna and a very rich amateur astronomer. He was also an ardent believer in astrology, which is why he hired Cassini. Next slide. This is where you'd find Bologna. Next. This is a modern photo of the observatory building. Next. At the Panzano Observatory, he was able to continue his research studies under the outstanding Jesuit scientists Riccioli and Grimaldi. Grimaldi later discovered diffraction. Next. In 1650, Cassini became a professor of astronomy and mathematics at the University of Bologna. Besides his obvious talents, he was supported by the Marquis Malvasia, who wielded a lot of political power in Bologna. Next. The University of Bologna was founded in 1088, so has been in continual operation for 934 years. This makes it the oldest continually running university in the world. Next. One of Cassini's predecessors as professor of astronomy and mathematics had been Ignazio Danti. He had been appointed in 1576. He had built a sundial, which instead of using a shadow to tell the time, used a hole in the roof as a sort of a big pinhole camera. The image on the floor traces the path of the sun as it moves across the sky. Next. Except the roof he used was on the Church of San Petronio, one of the largest Christian churches ever built. As you can see, it's pretty big. Additions to the building had blocked this enormous pinhole camera, so Cassini sketched a plan for a new and even larger one. The roof is 219 feet above the floor. This new and better version was apparently difficult to build, but using his plans, the rebuild was a success. Next. The much larger image of the sun's disks allowed him to measure changes in the sun's diameter as the Earth moved away and toward the sun. He concluded that the changes in size were consistent with Kepler's heliocentric theory, where the Earth moved around the sun in an elliptical orbit. He published his results in 1665. Next. Cassini was also interested in engineering and hydraulics. He served as an expert on river management to the Pope and was appointed as superintendent of the waters of the ecclesiastical states. The Pope actually asked him to take holy orders, but Cassini was more interested in his post as a professor, so declined the offer. Next. In 1664, Cassini was able to observe with powerful new telescopes made by the excellent lens maker Giuseppe Campani of Rome. He was the best maker of optical instruments of his age. He was an expert in grinding and polishing lenses, especially for very long focal length aerial telescope objectives. Apparently, he was also very secretive about his methods, only sharing his techniques with his daughter. When Cassini finally got to France in 1669, King Louis XIV of France ordered several long focus telescopes from Campani for Cassini to use at the Paris Observatory. These had long focal lengths of 86, 100, and 136 feet. In 1871, one of his 10-foot telescopes was tested and found to be quite good with a magnification of about 20 times. Next slide, please. Using these telescopes, Cassini was able to measure the length of the Martian day by watching the planet rotate on its axis. He was able to measure the length of day on Jupiter, discovered the bands and spots on Jupiter, and saw that the planet was flattened at its poles. I have looked at Jupiter many times through a telescope, some of them really excellent scopes. Often the view is similar to this image. I have never noticed that Jupiter was flattened at its poles and bulges at the equator. It is not that obvious, so the fact that Cassini noticed it is quite surprising to me. Next, please. But when I take this image and show it next to a 90 degrees rotated copy, the flattening is obvious. This photo was taken by amateur astrophotographer William Dombrowski. He calls himself the Wizard of Elton. Later in France, he would suggest that the Earth bulged at the equator. Bulged at the North and South poles. I will mention this later in the talk, but I was surprised that he didn't make the connection between Earth and Jupiter. Next. Very few scientists are paid to do pure science. Almost always there is some ulterior motive to scientific research. In the case of Cassini, it was astrology. People needed to know about the motions of the heavens so they could make better astrological predictions. But the governments of the world had another reason for knowing the sky, and that was navigation. If you know the sky well enough, you can know exactly where you are on Earth. But to find latitude, you not only need to know where the stars are, but when they are there. Galileo suggested using the moons of Jupiter to do this. Next slide. The moon that Galileo and Cassini were interested in was Io. It is closest to Jupiter and thus heads into the shadow once every 42 hours. If you could make a table that listed the future eclipses of Io, these could be used as a clock to figure out longitude. Later in the presentation, I will describe how this can be done, but right now, let's just look at the problems of making this chart. Next. The first challenge is that Jupiter is not always the same distance from Earth. Both the Earth and Jupiter have slightly elliptical orbits, but the main problem is we are not always observing Jupiter from the same spot in our own orbit around the sun. Here is a diagram from my childhood. It shows looking at Jupiter from E1 and then again at E2. You can see that the light from Jupiter will travel further getting to Earth at E2. Cassini noticed that light took 20 or 22 minutes longer to travel across the Earth's orbital diameter. At this time, the speed of light was thought to be infinite, so even though he saw it, he didn't believe it. He figured the timing difference must be caused by something else. Just a note from my high school years. When I first saw this diagram, I thought, how can you see Jupiter from E2 when the sun is in the way? Well, you can't. In this orientation, Jupiter is up during the day, and although we might see Jupiter through a telescope if we knew exactly where to look, we certainly couldn't see an eclipsing Jovian satellite. Next. 7 years later, this fine gentleman, Danish astronomer Romer, was working for Cassini at the Paris Observatory. He took Cassini's data and became famous for figuring out the speed of light. He only had two problems. One was that the timing was not quite correct, and the second was he didn't know the diameter of the Earth's orbit. He used the data that he had and came up with 211,000 kilometers per second. The modern accepted value is 300,000 kilometers per second. Romer's speed was 70% of the modern value. This is pretty close considering the data he had to work with. Next. The diagram earlier was impossible. This one shows a more realistic way of looking at the view of the satellites entering and leaving the shadow of Jupiter. The angles here are really exaggerated, but they'll give you the idea. I believe that they watch the moon disappear into the shadow. The problem with this is that it is not an instantaneous event. Using the poor telescopes available at the time would also make this tough. The biggest source of error was not knowing how far away Jupiter was from the Earth. This made charting future eclipse times very difficult. Next slide. In 1668, Cassini was invited to Paris by King Louis XIV. He needed the permission of the Senate of Bologna and Pope Clement IX. They believed he'd only be gone for 2 years, so they gave their permission. Have a look at the king's very attractive legs. Next slide. He arrived in Paris in 1669. He was 43 years old and would spend the rest of his life in France. Next slide. In 1671, he became head of the Paris Observatory. In 1673, he became a French citizen and changed his name to Jean Dominique. In 1674, he married the daughter of the Lieutenant General of the Count of Clermont, who was rich and powerful, and his bride came with a very generous dowry. They had 2 sons, the youngest of which succeeded his father as the director of the observatory. He is generally known as Cassini II. 4 generations of Cassini held the position of director of the observatory. Surprisingly, they were known as Cassini I, II, III, and IV. Next. This handsome gentleman is Cassini's great-grandson, known as Cassini IV. Next. These long telescopes are some of the scopes produced by Giuseppe Campani of Rome, bought by King Louis for Cassini. Next. This image shows the scopes being used at the Paris Observatory. Apparently, the image produced by these telescopes was pretty good, but I can't imagine how you found your target, as the field of view must have been minuscule. Next slide. In Paris, he continued to make new discoveries. He was the first person to observe the 4 brightest moons of Saturn. He discovered the gap in the rings, which we now call Cassini's division. He correctly surmised that the rings must be made of smaller particles in orbit around Saturn. Next. He drew a map of the moon, which remained the best map available until the invention of astronomical photography. Next. This moon maiden can be found on his map. It is not known if Cassini did this on purpose or by accident, or whether it is a joke courtesy of his engraver. Next. If we look at the subtle image of Saturn, the Cassini division is obvious. The rings are angled to give us a good view. The gap is 3,000 miles wide, and the focus is perfect. Many of us have looked at Saturn through pretty good telescopes, and if the seeing is not good, the division can be hard to see. Next. Given the optical technology of 1670, what did Saturn look like to Cassini? Not only did they need to figure out what shape to make the lenses and then to grind them to that shape, they needed to develop clear and bubble-free glass. It looks like Giuseppe Campani had it figured out pretty well. He solved the problem of color splitting when they go through a single lens by making the telescopes extremely long focal lengths. His lenses were 4 or 5 inches in diameter, with focal lengths ranging from 10 to 100 feet. These were f30 to f240 lenses. Next slide. This question was also asked by Julian Losey, an optical scientist at the University of Arizona. He led a team that studied the optics available to Cassini. They found the quality of the lenses was excellent. In one lens, the Strehl ratio was 0.94, where 1 is perfect. This is good even for modern lenses. Next slide. Using their findings, they produced a simulated image of what Saturn would look like to Cassini. As you can see, the division is visible, but not exactly obvious. Next slide. It is now time to discuss the connection between Cassini and the map of France. Next slide. King Louis XIV and his officials, primarily Jean-Baptiste Colbert, the Controller General of Finance, decided for political, financial, and military reasons that they needed an accurate map of France. This was a big problem, as France was the largest country in Europe with an area of 600,000 kilometers. And it also has a land boundary of more than 6,000 kilometers. Many of the countries on the other side of this boundary were not friendly to France. It was decided that a map of this magnitude would require both surveying and astronomical methods. Who would be better at this than Cassini, as he is both an astronomer and a mathematician? Next. Before I go any further, I want to briefly review how we measure the Earth. I do realize that you all know this, but a reminder won't hurt. Latitude refers to the lines that run east and west around the Earth parallel to the equator. They are measured in degrees up and down from the equator. Here in Ottawa, we are about 45 degrees north of the equator. Longitude refers to the lines that run north and south and pass through both the north and south poles. Zero longitude passes through the Royal Observatory at Greenwich, England. I guess when you rule the waves, you get to choose the starting point. Ottawa is about 76 degrees west of Greenwich. Next. Here is a line with the lines of latitude shown, but how do you measure them? Next. You cite the elevation of a star from your position on the Earth. You measure the angle from the surface of the Earth or a pendulum aiming straight at the middle of the Earth. You then compare that angle to the angle that a person standing on the equator would get. Stars are so far away that the light arriving at them is parallel anywhere it hits the Earth. Your latitude is the difference between your reading and that of the person standing on the equator. We have two obvious problems with this method. First, you need somebody standing on the equator to give you the reference reading. And second, you both need to take the reading at the same time as the stars will be moving across the sky. You actually don't need somebody standing on the equator. You just need to know how high your particular star would be if you were standing on the equator. You can read that value from a chart that somebody else prepared. The timing problem can be solved by measuring the star when it is highest in the sky. That will be when the star is straight south of you and is crossing the meridian. As you watch the star, it will climb and then start to descend. When it changes altitude, you make your reading. At the moment the star is at its peak and is traveling parallel to the horizon, it is traveling here parallel to the horizon. So timing errors produce only small altitude errors. Next slide. Here is a globe with the lines of longitude shown. Measuring your longitude on Earth is a much more difficult problem. Next slide. This is a view of the Earth from above. That is, we are standing looking straight down on the North Pole. The procedure is somewhat similar to finding latitude. You cite a star to the east or to the west, as in this illustration, and compare your value to the star's elevation with the value measured by someone standing on the prime meridian, or wherever you wish to start your measuring. Again, you would need a chart with the altitudes of suitable stars as measured at the prime meridian, and we compare our altitude to those. But the timing problem is really tough to handle. You have to remember that in the 1600s, they didn't have accurate clocks. If you were standing on the Earth somewhere near the equator, you'd be zipping along about 1,600 kilometers an hour, or 28 kilometers a minute. That means your longitude measurement will be incorrect by 1,600 kilometers for every hour that your clock is wrong. Even a mistake of 1 minute results in a 28 kilometer error. When you are on a sailing ship in the middle of the ocean looking for a tropical island the size of a pinhead, this error matters. 48. Next slide. As I mentioned earlier, Galileo had suggested using the eclipsing of the moon Io behind Jupiter as a timing method. Cassini spent much of his time trying to set up tables of these eclipses, but couldn't accurately predict their occurrence due mostly to the Earth being different distances from Jupiter as it spins around the sun. Next slide. But if you send people out to observe a star and they all do it at the same time, you can find the relative longitudes. If you are staying in the same country, this should be possible. Pick a star, tell the people you send out to record its elevation exactly when Io disappears into Jupiter's shadow 2 weeks from tomorrow. Then they all gather back together and compare data. The relative longitudes can then be calculated. This is what Cassini did in France. They calculated a bunch of longitudes in the country and then used good old-fashioned surveying techniques to triangulate all the towns and rivers in between. Next slide. For political reasons and the fact that it was close to home, they started with a map of the area surrounding Paris. Next slide. They also mapped the coastline of France. You can see the prime meridian going through Paris. What a surprise. Because they were able to measure the longitudes accurately for the first time in history, they got the west coast of France in its correct location. The dark line is Cassinis and the fine line is what they thought it was before. You can see that Cassini managed to shrink France. This did not make him popular with the king, who declared, "Cassini has taken more of my kingdom than I have won in all my wars." Next slide. This map-making project took way longer than and was much more expensive than they first planned. The king ran out of money and the new kings were not interested in paying. The citizens of France were suspicious when strangers showed up in their villages with the weird-looking instruments and were asking many questions. They often got no help whatsoever. Eventually, the map making was privatized and they sold shares in the endeavor. It also took 4 generations of Cassinis to almost get the map finished. That is Cassini 1 to Cassini 4. By the time Cassini 4 rolled around, the king had been beheaded during the French Revolution. Apparently, Cassini narrowly missed the same fate, but the revolutionaries did nationalize his map, which really annoyed Cassini 4. When done, the map had grown to 182 sheets. Why, you ask, do I have a picture of Napoleon on this slide? In 1814, almost 20 years after Cassini 4 lost control of the maps, and almost 150 years after Cassini 1 started the project, Napoleon was getting ready for his last battle before being exiled to the island of Elba. He and his officers were billeted with the local priest. The priest was astonished. They knew all the names of the local villages. He was sure they were from the area themselves. They then showed him Cassini's maps showing all this information. The maps were so good that even Napoleon used them for battle planning 150 years after they were drawn. Next. Cassini's tables of the eclipse of Jupiter's moons were now being used to calculate longitudes all around the Earth. This was especially important to sailors. By the way, the English solved this problem by inventing a better clock. This was constructed by John Harrison in 1761 after 30 years of development. His reward was £20,000, which would be worth $2.5 million today. The trouble he had collecting this reward is a great story in itself. Next slide. In 1687, Newton came up with his law of universal gravitation. This law predicted that the Earth would be flat at the poles and bulging at the equator. Cassini did not like this idea and refused to believe it. He felt this way even though he had seen the flattened Jupiter. Cassini was a traditionalist and in general did not like new theories. Newton was also a rather pompous Englishman, and I wonder if this influenced Cassini's thinking. Next slide. Cassini suggested this could be tested by measuring the degrees of latitude at different places on Earth. You can see from this modern diagram that at high latitudes, the normal at the surface of the Earth does not point at the center of the Earth. This would make a degree at the pole longer than at the equator. A degree of latitude at the pole is 111.7 kilometers, and the equator, a degree of latitude covers only 110.6 kilometers. This is the difference of 0.9 kilometers or 900 meters. An easy way to think of this is that a circle with less curvature, flatter, has a longer radius than one that is more curved, bulges. But the test was never attempted because no one would pay for it. Next slide. In 1672, Cassini sent Jean Richer, one of his assistants, to Cayenne, French Guiana in South America. Yes, this is where the French penal colony of Devil's Island was located. It is almost 8,000 kilometers from Paris and almost 5,000 kilometers south. Cayenne is latitude 5 degrees north and Paris is 49 degrees north. Next slide. Cassini and Richer simultaneously measured the position of Mars in the sky. When Richer returned to Paris with his data, they were able to calculate using parallax the distance between Earth and Mars. Since Kepler had already figured out the ratios of all the planetary orbits, they only needed one measurement to calculate all the others. This was the first time planetary distances had been measured accurately. Next. While in French Guiana, Richer calculated the length of a pendulum that swung with a period of exactly 2 seconds. He found this pendulum was 2.8 millimeters shorter than the pendulum in Paris that also had a period of 2 seconds. This agreed with Newton's theory of universal gravitation, which suggested that the Earth was flattened at the poles. Cassini thought they were both wrong. Next slide. In 1695, Cassini returned to Italy for the first time in 26 years. He took with him his 18-year-old son, Jacques Cassini. They visited Genoa and Bologna. When in Bologna, they repaired the pinhole sundial at the Church of San Petrione. Next slide. By 1709, Jacques Cassini had taken over most of his father's duties, including as head of the Paris Observatory. Cassini's health had started to fail, and his eyesight got so bad that by 1711, he was effectively blind. This is not a good state for a visual astronomer. His personality was such that he was able to accept his failing health with gentle good humor. He died in 1712. Next slide. I need to tell you about this illustration. It was the image of John Boots, who used it to illustrate his article on Cassini for his high school newspaper. The paper is called The Knight Errant, and the school is in St. Louis Park, Minnesota. A knight errant is one of those knights that wanders around the countryside doing good deeds. Next slide. During his life, Cassini accomplished many things. Some of his achievements are, he used observations and parallax to find the distance to Mars. He found 4 of the moons of Saturn. He discovered the division in Saturn's rings and correctly realized that the rings were made up of many small particles in orbit around the planet. He shares the discovery of the Great Red Spot on Jupiter with Robert Hooke. He found the length of the day on Jupiter and Mars. He was the first to observe differential rotation within Jupiter's atmosphere. He mapped the moon. He mapped France using astronomical determination of latitude and longitude. These maps led to the concept of France as a country rather than a collection of districts. Next slide. Cassini has been given many honors. Some of these are the Cassini division of Saturn's rings, Cassini craters on the moon and Mars, the Cassini spacecraft, which spent 13 years studying Saturn and many of its satellites, observed Jupiter and the heliosphere, and best of all, many statues of Cassini, one of which is in the Musée du Louvre in Paris. It's easy to criticize Cassini for his theoretical mistakes, but he was not a theorist. He was a brilliant observer. Have a great day.
Beauty. Thank you, Bob. Covered a swath of history and too many events to readily enumerate. It's a complex story of an overachieving family. Again, I'll kick off the Q&A. Again, displaying my ignorance. On your diagram where Cassini's assistant had gone to Cayenne, there's 2 labels, and one of them is the massive Bob, and the other one is Bob's trajectory or amplitude. And I'm wondering if that's self-referential.
Yeah. Basically what he did was he he made a pendulum, which they call a second pendulum, because in those days, an amplitude was only one travel across. But today, an amplitude starts on say the left edge, goes out to the right edge, and comes back, and is 2 seconds. So in actual fact, it's a pendulum swinging back and forth across the thing. And I say they measure 1. To get an accurate answer, you might measure 100 and divide by 100, reduce your error by 100 times. Yeah, and he found the pendulum was shorter at the equator. Who knew?
Are there any other questions out there? Please slot them into the Q&A box in order to give Bob time to go to bed or to get out observing or whatever.
Looks kind of foggy outside right now.
Yeah, it's not great, is it?
No.
So, Bob, I don't see anything further popping up. Thank you
Okay.
for that.
You're welcome.
This confluence of astronomy, astrology, navigation, and surveying is something that I'm keen to keep exploring during these presentations. So just as a message to any of you others out there who'd like to tackle things like Cook's voyage to Tahiti for the transit of Venus in 1769 and so on, I'm open to them. So thanks, Bob, and I guess we'll see you during the observations. Thanks.
Good enough.
And with that, Chris, we get to the trivia challenge. Again, it's a bit different this month, and it's not precisely about astronomy or our fabulously well-provisioned website, but it is about RASC Ottawa. And so next slide. The question is, who is this man dressed up? I can't tell whether he's a hobbit or a druid, but why is he dressed like this? When was this allowed to happen? And this was at a RASC meeting, and I'll give you a hint that it was well over a decade ago. So you've got 5 minutes for our bio break and to try and dredge up the memories of who was the hobbit druid of Ottawa.
Sounds good.
Katie, so the question was, who is this man? Why is he dressed like this? And when was this allowed to happen? And next slide, please, Chris. I have no idea. I found this while I was archiving old video footage of meetings, and this one is from July 2007. And apparently the event was in celebration of the summer solstice, and hence the theme was dressed like a druid for the night. Who is the individual?
There have been many suggestions in the chat room who it is. They're all suggesting the same person, and he is an attendee in the meeting. I'm waiting for him to speak up.
Stephen.
I will have to open Stephen's microphone as an attendee to give him the opportunity to defend himself.
I think that's necessary. I think it's humane.
Stephen's mic is on if he's able to speak.
Okay, so apparently the shame is too much. So there goes whatever respect we had for Stephen on any number of fronts. But yes, fun times at RASC Ottawa in 2007. Thank you. Next slide. We go to Andrea now. So again, many of you know Andrea from her frequent contributions to the observing sessions, the observation reports. Her story of the development towards tonight's presentation is an interesting one, with the fact that it relied on her daughter having to be at home with her mother when NeoWise was coming along, and Andrea actually got to learn how to get her DSLR up and out and taking the types of photos that she's going to be talking about tonight. So Andrea, on an introduction to shooting the Milky Way. Thank you.
I'm going to share my screen just a second. Okay.
We
Okay,
see
so
your
what?
slides well. Mhm.
Okay, great. Thank you. The purpose of this talk is I'm hoping to encourage people to get out your regular cameras and try to take pictures of the Milky Way. This is the time of year to do it. There are warm summer nights. And when we talk about Milky Way season, what we are really talking about is the core of the Milky Way, which is a very, very bright segment that we see at the moment. I'm going to get my little pointer out. Obviously, this is the very brightest part of the Milky Way, and you'll see a little red spot, and that is the Lagoon Nebula, M8, and it's one of the very brightest nebulas in the Milky Way. What I am going to talk about briefly is where to look, when, what camera lens you should use, and how to take a single shot. And modern sensors can really take, in a single shot, can get a pretty good picture of the Milky Way. Once you have learned how to do your basic shot of the Milky Way, then you can start to look at things like stacking and using Photoshop or other software to enhance the image. And then there are even further steps you can take in your development. So right now is the time to look, and you will see the Milky Way from the southeast into the southwest. In early March, it'll be only rising. The core rises very early in the morning, but that rising happens earlier and earlier and earlier throughout the summer. So right about now, you will see the Milky Way rising around 11 o'clock p.m., midnight. By the end of summer, as soon as it's dark, you can see the Milky Way. And if you are using a planetarium app on your phone, such as Stellarium or Sky Guide, if you put in Messier 8, which is the Lagoon Nebula, it'll take you straight to the portion of the Milky Way, and you should be able to use your app to find the Milky Way. Where can you best go to take photographs of the Milky Way? And there's really no way to get around this. You have to go to a dark place. I have tried everywhere around Ottawa. I went to the suburbs. It's almost impossible to get a nice image with light pollution. This picture that I have up here is from a website called lightpollutionmap.info. It allows you to zoom in into your area, and it's really important that you try to find a dark location. And particularly in Canada, you'll see we're pretty lucky. We have a lot of dark areas, but you want to make sure that you don't have a bright city to the south, because that's where the Milky Way is. It'll be to the southeast, southwest. This requires scouting in advance. And I do a lot of my scouting in advance during the daytime, but then sometimes it's also worthwhile doing some scouting at night. This was one of my first adventures out to try and shoot the Milky Way, was up in cottage country, west of Ottawa, and near Crow Lake. So it should be pretty dark. It was quite dark on the light pollution map. But when I got there, you can see down in the lake, there is a bright yellowy area, and that I believe was the city of Kingston. And I was miles and miles away, and there was a lot of light pollution. Similarly, you could actually see a street light sending a yellowish light coming in from the side. And that can sort of spoil everything too. You know you have light pollution when it comes out in your camera is a bit yellowy, and you can sort of fix it a little bit in post-processing, but you won't get the darkest sky. So you need a dark sky. Sometimes you can't scout in advance, but if you can, or if you're at a cottage or a lake, that is the best place. And you will get your best images in a dark place. So now, what kind of camera do you use? Most people who are doing imaging with for the Milky Way will use what we call a DSLR, which is a digital single lens reflex camera, or mirrorless. And I'll show you a picture of mine, but basically these are cameras where we can take off lenses and change them. And you'll see why lenses are important in a moment. There are some smartphones currently that are able to take Milky Way photographs. They are typically quite modern cameras, and they usually have a special app on them which will allow you to do the 3 things that any camera must do. It must be able to shoot long exposures, up 10, 20, 30 seconds. You have to be able to raise the ISO, which might be called the gain. That is what allows you to gather even more noise, signal. And that's not quite the right explanation of it, but you want to be able to shoot at a high ISO, long exposure. You would like to have a camera that can shoot in RAW format. Typically, when we take pictures with our cameras, you get JPEGs, and that is a compressed format. If you can shoot in RAW, then you can work with the data and you don't lose any data in post-processing. So some camera phones, if they have an app that allows you to shoot in RAW and take long exposures, you might be able to use them, and people do use them. Google Milky Way with a cell phone and you will see a lot of information. You should have, whether it's a cell phone or whether it's a DSLR, you should have a tripod. The tripod is required because of the long exposure. You don't want any shake, any blurring. Ideally, if you have a remote shutter as well, that can also help reduce camera shake and blur during a long exposure. Finally, and very importantly, you would like to have a wide angle lens that is a fast lens. So I'm going to talk a little bit about lenses. For your first Milky Way photography, I would suggest taking whatever lens you have and opening it, making it as wide as possible. If you have prime lenses, use your widest angle lens, such as 14 millimeters up to 24 millimeters. We talk about a fast lens. What that means is all of the camera lenses have an aperture. And the bigger the aperture, the lower the number. So for example, a lens that is an f1.4 or f2.8, those are called f-stops, is how big your aperture of your lens can be. With astrophotography, you're always wanting more light, so you want the biggest aperture you can. Sometimes when you just have a lens that came with your camera, it may not be this fast. It may only be a 3.5 aperture lens. You're going to use it anyway. So open it up as wide as you can. There are many inexpensive lenses out there nowadays. Rokinon and Samyang are 2 very popular brands of lenses for astrophotography, but they are fully manual. There's no autofocus and there's no auto aperture, which for most astrophotography work is fine because you do want to use a fully manual system. There are some fast zoom lenses out there as well, and a zoom allows you to do a different focal length, 15 to 30, and a lot of people use those lenses as well. The key is, and this is really important with Milky Way photography, is that your lens will define your field of view. So for example, this is a very wide field of view. It's a 14 millimeter lens on a full frame camera. Some of you may have a crop sensor DSLR camera. That makes the image a little more narrow, typically. The nice thing about a wide angle lens is that you can put it on a tripod, open up the aperture as much as you can, and then you can take a single shot of up to 30 seconds without the stars moving. And that's the key. Your lens defines how long you're able to keep your shutter open without star trails. So here is a very wide angle lens. You can do up to 30 seconds. This is an image shot with a narrower lens, 35 millimeter lens. And as you can see, the difference is, if I go backwards, you're zoomed in on the Milky Way. It's a little more dramatic. It's much bigger in the picture. But the trade-off is you can only expose for 15 to 13 seconds before the stars start to move. So you have a nicer, more zoomed in look to the Milky Way, but you can't collect as much light. Similarly, if you even went deeper into the Milky Way, 50 millimeter lens, the Milky Way is very big, very dramatic, but if you're using a tripod, you can only shoot up to 5 seconds without star trailing. So I'm just going to go back through this one more time. This is a narrow field of view. This is a little wider, you can shoot longer, and this is the widest. And so if you're going to start out with Milky Way photography, I recommend you go the widest angle lens you have and see how you can shoot for 30 seconds. All right, so you have your camera, it's on a tripod, you're outside, you know where to look for the Milky Way, you've opened up your lens as much as possible, it's time to take the picture. What I recommend is you try to get your ISO up at least to 6400. If you're dealing with a lens that doesn't open up very wide, you might want to bump your ISO up a bit. You need to focus on the stars. That sounds easy, but it's actually a bit tricky. So some people, like I tend to take some practice shots and make sure I'm focused, and then I often tape the focus down so that it doesn't move for the rest of the night. Again, the key is you want to expose for as long as possible with the widest aperture, but not too long so that you get star trailing. And that's why you have to know something called the 400 rule. And the 400 rule says, if you take your lens focal length, for example, a 20 millimeter lens, 400 divided by 20 gives you the number of seconds you can expose before star trailing. So if I have my 20 millimeter lens out, I know that I can shoot for about 20 seconds before I get star trailing. And then once I take my image, go ahead and take 10 of them of the exact same image, take 10, because you might want to do stacking later on. So this image was one of my very first Milky Way shots. And as you can see, this is something you might see in your first attempt. This is a bit, it's a bit, what's the word? It's a bit faded, as you can see, because I've lost a bit of contrast due to light pollution. I didn't get as far away from the city as I would have liked to. There's a lot of light pollution here from Ottawa and more pollution here from Carleton Place. I was up near Pakenham. So you can see the Milky Way, and I got a picture of it, but it's lost a bit of contrast due to the light pollution. Another thing that you can see is my horizon is slanted. And I have a trick for that because, you know, you're so busy worrying about the stars, you forget to fix your horizon. So once you've done this, try giving it a shot, shoot for 30 seconds, and then look and see if your stars are trailing. And if they are, you just have to reduce it a bit. But any camera that you have on a tripod, if you point it in the right place, hopefully you will get a Milky Way image. And that's just sort of the beginning. So these are pictures of my setup. As you can see, it's nothing very complicated. I have a tripod. You want it to be solid. I have, this is a DSLR, it's a Nikon. And I have a Rokinon lens, and it's a 1.8. So it's a pretty fast lens with 20 millimeters. So I'll shoot maybe 15, 20 seconds with this lens. And then I have an intervalometer. And this is something I pick up off Amazon. It's specific to my Nikon, and it allows me to set a sequence. 15 shots of 20 seconds, 13 shots of 30 seconds, whatever I want to, and then it runs the sequence. I don't have to touch anything. Okay, so now that you've tried a single image and maybe you followed my advice and you took 10 images, now you can try something called stacking. And stacking is kind of a nifty trick that really makes a huge difference. There is stacking software that will put your 10 images together. It'll stack the sky separately from your foreground and then recombine them, which is really neat. Because if you don't have stacking software, your foreground will stay in one place over the sequence, but your Milky Way moves sideways. But somehow these pieces of software, they can do this all by themselves. So for Windows, you can pick up a software called Sequator. It's totally free and it works extremely well with for stacking images. The Mac users, unfortunately, you have to pay, and I'm not sure there's a typo in my slide, but last I looked, it was around $55. You take your 10 images, you load them up into the software, and it will stack them all for you. And there are a lot of YouTube videos on how to use at least Sequator. I'm not so sure, probably also Starry Landscape. And I guess in this slide, I decided to talk about a couple of other pieces of software that I use quite a lot. Stellarium, both the computer version and on the mobile. PhotoPills is a way of planning your Milky Way shots. Sky Guide is a very nice app for finding things in the sky. And Astrophotography is my very favorite weather app, because you need a clear sky for this. So for example, this image here is a stack. I gotta have to move. Hang on, I got to move. There we go. I took 10 images of 13 seconds with a 28mm lens. So using the 400 rule, you would take 400, you divide it by 28, and I think it was 15 seconds or 14 seconds. And then I stacked it in Sequator. That being said, as much as it's pretty easy to take a photo of the Milky Way, almost all Milky Way shots benefit from some work in the on the computer with your Photoshop or Lightroom or whatever image processing software you use. And there are free ones out there. I just don't use them because I already had Photoshop. We're not playing or manipulating with the image, but generally what we are doing with the Milky Way is we're increasing contrast. We're raising the brights, making the brights brighter and the darks darker. You might want to do a little noise reduction or lens correction as well. For those of you who don't know, noise is that speckliness you see all around your image, and stacking helps reduce noise. I am going to tell you about Christine Rose Photography. She's a Canadian astrophotographer. She lives in Nova Scotia, and she generally runs a free Milky Way photography course a couple of times in the summer. I'm about to lose my voice here. If you Google her name, you'll probably find out about her course. It's a free course that leads into a paid course, but it gives you a lot of tips to see if you really want to do this kind of astrophotography. And she covers some basic editing in Lightroom for your Milky Way as well. So for example, when your images come out of Sequator, you just get an image like this one. This was a shot I took at the lunar eclipse a couple of weeks ago. So normally when there's a full moon, you don't do Milky Way photography, but of course during the lunar eclipse, the sky got very dark and you're able to see a bit of the Milky Way here. This, obviously I have the information here. I did 15-second shots. I used an ISO of 1600. I'm not sure why. Normally I would recommend you would use a little higher ISO. And I took about 10 shots and I stacked them in Sequator. And it looks very pretty and it's very nice, but if you do a little work in Photoshop, it looks a little more dramatic, and you can do things like reduce the saturation of light pollution, you can increase contrast, and it makes almost all images look a little better. Oh, good, we're getting near the end because of my voice. If you like this kind of work and you're enjoying Milky Way, there definitely are lots of next steps to progress. One of the things is to get an Astro modified camera. I'm using one. You may have noticed that a lot of my images went very pink, and that's probably why. I'm not entirely certain I like the pink, but that's another story. Some people do Milky Way photography on a star tracker, and I highly recommend you don't do that to start. It's a lot trickier than it looks, particularly if you have a foreground, because when you track the stars, your foreground is a mess. So you need pretty advanced skills in Photoshop to deal with blending, and you will almost always have to do a separate exposure for the sky, and a separate one for the foreground. That's another step to take. A lot of people do very fancy lighting scenarios for the foreground. You can do a long exposure, you can do a moonlit foreground, you can do light painting, and it becomes very, it can be very complicated. You can also do panoramas and vertiramas. I do a lot of vertiramas where I take one image and then I'll take another one directly above it. I only do two, but it makes a big difference with your Milky Way photography. And then you have to get into a little bit of more Photoshop because you'll be doing with masks and different layers. So you can, it's an endless source of fun and inspiration. So I hope I've encouraged some of you to at least try to get your camera out and see if you can try to capture the Milky Way yourself with your normal cameras. And if you have any questions at all, I'm happy to speak directly to anybody here. And that's my email. So I'm going to stop the share now.
Andrea, thank you. And sorry for your throat. I hope you haven't got Chris's COVID. I will lead with my dumb question. Given that the stacking software is smart enough to recognize and account for the exposures of foreground objects, is there any prospect of such software similarly dealing with distant horizon light pollution, the type that you were getting from Kingston when you were at Crow Lake?
Sequator has an option where it does kind of try to deal with things like light pollution. It tries to deal with, there are a few buttons you can play with to try to increase the contrast. The best way to, I think the best way is to avoid light pollution, because light pollution permeates your whole image. It'll reduce contrast across the board, and it desaturates, and the yellow comes in and everything gets messed up. So, I mean, maybe the software will do it one day, but it's much nicer and you'll be much happier if you just don't have to deal with the light pollution. But there's tricks and techniques to do it, and they try to automate it. Unfortunately, sometimes it works, sometimes it doesn't.
Alrighty, in the chat we've got Chris stating, thanks Andrea, you're definitely motivating me. I hope that's a broad sentiment out there. Is there any other questions for Andrea before I say thank you and move us along?
Thank you.
Okay, I don't see any other questions, so thank you. And I will move us along. Chris?
Can I hijack the meeting and go back to this slide?
Yes.
And help people's memory with this image that was submitted by Brian McCullough during Andrea's talk.
Now we can see the culprit.
The culprits.
We can see the many culprits.
Thank
come
you,
on,
Brian,
give us-
for submitting that.
Okay, so give us the story, Chris. You were there.
If I can get Brian's attention and give him the microphone, he can explain it. Brian, your microphone is turned on. Waiting. He
These
must have
people are
stepped away for a minute.
really hopeless. I think we just need to move on, Chris. So that's both.
Yeah, but obviously that's Brian on the right, Rick Wagner in the red shirt, Stephen in the black druid costume, and I'm struggling whether that's Ingrid on the left. I can't remember for sure who's on the left. Someone will pitch in and help.
All righty.
Oh, and Brian's replied on the chat that he has no ability to chat right now or to turn his microphone on. Okay, with that, sorry for that hijacking, but I thought it was a fun submission. We can move to the next phase.
Our observation reports. Next slide, please. As you can see, here's the sequence that individuals will be called. I'll be speaking for Natasha Blazevic's submissions. a new contributor. So yeah, let's get moving. First off, Jim Sophia, and I will lead this with an apology because Jim's submissions were actually for the May meeting and I screwed up. And so
No problem. No problem there. Okay. So this is a crop image of NGC 3242, the ghost of Jupiter, which is also known as the Eye Nebula. It's a planetary nebula, approximately 1,400 light years away in the constellation Hydra. You may see hints of the central star or white dwarf in the center of this image. It was taken with the Celestron 8-inch Smith-Cassegrain camera with a UHC filter and the Malincam Skyraider DS10C Tech camera. Next one, please. We are in a cycle of increased solar activity, and this image of the solar surface was taken on April the 20th, featuring sunspot activity amidst surrounding plages or bright regions of higher temperature, which is typically found near sunspots. Sunspots are cooler, darker areas of intense magnetic activity on the surface of the sun, which is blocking the outward flow of hot gases. You can see the direction of the swirling plasma around this area, which is directly influenced by the strong magnetic activity. Sunspots may accompany a variety of other solar activity like coronal loops, flares, coronal mass ejections, and prominences. This image was taken with the Lunt 60 millimeter hydrogen alpha solar scope and the Malincam Skyraider camera. Next one, please. Using the same equipment, here is a montage of two close-up stacked images. A group of solar prominences taken first, and then later merged with a stack image of the surrounding solar surface taken several seconds afterward, just by adjusting the gain and time exposure on the fly. So this composite image was post-processed using Topaz Studio 2. Thank you.
all righty. Whoops, yes, yeah, righty. Thanks, Jim.
You're
Now,
welcome.
okay, so Natasha Blazovic sent these photos in within the last couple of days, and it's a little saddened that she can't join us tonight, but that's apparently a problem of having children, and it might be her fault, but we can't blame her for it. So this is a little bit unusual in a couple of senses. The first image here is one that she captured of M106 using the SLU remote observing service, pay to play access to remote observatories and so on. And in these observation sessions, we normally don't encourage contributions that aren't made or developed using individuals or members' own equipment. But in this case, I've opted to make a change to that policy in the sense that it's Natasha's first contribution and is to be encouraged, and we want more of it. And she's got some more photos coming up in a sec, which she did take from her own backyard. Secondly, obviously remote observatories give Northern Hemisphere observers access to parts of the sky that are difficult to access from here. And even Andrea's Milky Way contributions, to speak from experience, certainly improve as you go further south, and those features are overhead. So maybe it's just inevitable that in our future there will be further observations by members using remote technology. And I think inevitably that needs to be encouraged as well. Our purpose is to, as a society, is to motivate people's understanding and interest of the night sky and these are tools that are going to get us there. So next one, please, Chris. Okay, so Natasha's other contributions were from her backyard over in Gatineau during the super blood moon, using an iPhone attached through a sonotube Orion telescope. And I will quote her here, "I haven't figured out how to properly mount a camera to either of my telescopes, yet the iPhone is pretty handy in the meantime." And she refers to a trick she learned from Mike Banks at a RASC meeting involving pictures of Jupiter. And I think next slide, Chris. As you can see, not a bad shot for the equipment at hand and the sky conditions that night, which were somewhat cloudy. Because it was such a glorious experience, I created some astro art and digitally painted my experience, which is what I watched the eclipse. The lilacs bloomed and perfumed the whole garden, and in the morning all the blooms were open. Crabapple, apple and lilac, an assault of bee-friendly dandelions. It was sensational. My twin toddlers and I also planted some space-flown tomato seeds. She doesn't say where she sourced them from, but it's from the Tomatosphere project. And although they were long overdue to sprout, the morning after the supermoon, they sprouted in full force. So obviously Cassini was right about this astrology stuff and that lunar eclipses promote plant growth. So Chris, I think with that, we can move on. And
this one
finally,
additional image.
And finally, this image of Natasha of the Eta Carina Nebula, well into the southern hemisphere. Again, something I'm very, very familiar with. Again, using a remote telescope. And I will leave it at that. There's no way any of our members here would acquire such images without the travel involved to get into Chile or Australia. So that's my rant. Move on. Andrea.
Okay, so this was, I've just started doing solar imaging myself, and this image was taken from my backyard, and it was on May 13th, and there was just so much happening on this day. And this is with a lens 40 millimeter, so smaller than Jim's telescope, and there are several giant large sunspots. There were prominences along the edge, and this was taken with my guide camera, which is hysterical. So I have a ASI 290 mini guide camera. It's about this big, and I did a mosaic, and the mosaicing was probably the hardest part, but I was pretty impressed. And there's definitely, and a couple days later, there was even more activity. So it's definitely a really busy and interesting time to look at the sun. Next, please, Chris. Okay, so I have 3 galaxies that I shot in April, and so I'm just going to talk about all 3 of them, the equipment. So I used a Celestron C11 scope, 11-inch Schmidt Cassegrain. I used a focal reducer to reduce the focal length to 1,960 millimeters, which is still pretty long focal length for me. And so these are my first shots doing that. At that focal length, I decided to use an off-axis guider. So it was my first time doing an off-axis guider. And also I did some imaging with a color camera and some imaging then a few hours with a mono camera. And some days it worked and some days it didn't. So I can't tell you exactly how many hours I have on each of these. I can tell you all 3 of the galaxies are in the constellation Canis Phenetici. And yeah, so they're all in the same neighborhood. This one is NGC 5033. It's called the water bug galaxy because it looks kind of like a bug. It has really quite pretty color. The arms are definitely blue, full of the young hot stars that we heard about galaxies earlier, and the central core is very yellow. Next one, please. This is I made up that name, the rectangle galaxy. It's NGC 449, and it's called a Magellanic type. galaxy, which I didn't know we had any Magellanic type galaxies in the Northern Hemisphere. I didn't get a lot of time on it. I'm still learning, and not everything goes well with the long focal length, but it's a pretty cool galaxy, and it's a rectangle, so that's fun. Next, please. And this is M94. I should have mentioned that the rectangle galaxy and M94 are in the same group, the M94 group. It's about 16 million light years away. And M94 is fun because it has sort of an inner core, then there's like a very bright middle core, and then there's the faint outer dust lanes that can be tricky to get. And I shot it last year with the Hyperstar, and it was great. And I thought I'd try it again this year, and it turned out quite nice as well. Next, please. Oh, and this is my Venus image. I worked on Venus for many, many weeks, and this is as good as it got, but I was pretty happy with Venus. This was shot in early April, pretty early in the morning. As some of you know, because Venus is so close to the sun, it's very low on the horizon, and the seeing is not very good, so it's very full of vibration. But I did manage to use a IR filter. I had a UV filter, that didn't work. But the IR filter gave me a reasonable shot, and I stacked it up, and I finally got the edge. So I was pretty happy to finally get a stacked Venus picture. And that's it.
Hey, beauty. Thank you. And over to Oscar.
Hey, good evening. So I'm going to present a number of images here tonight. This first one was the totality phase of the lunar eclipse we had on May 15th into May 16th. Paul, myself, and another friend ventured down to Beveridge Locks between Smith Falls and Perth to try to dodge some of the weather we were having here in Ottawa. Clouds during an astronomical event in Ottawa, go figure. We also did happen to run into Andrea at the very same site doing the exact same thing. Next slide, please. So we can hit play there. So this is the same during totality as well. I took a little, not a video, but I stitched together a number of exposures here to show the moon occulting that double star there on the bottom left of the moon. That's HD 138268, which is a double star in Libra. And that occultation happened at about 1:02 in the morning on the 16th of May. So all the images for this were taken through, were all 5-second exposures through a Canon 60DA on an 8-inch Celestron Edge HD with a focal reducer. So I believe the focal length was like 1422 millimeters. All right, next slide, please. This is Markarian's chain. So this is a chain of galaxies which are a part of the Virgo cluster. I think Nathalie mentioned the Virgo cluster earlier in her presentation, so it was kind of neat. This group contains a number of well-known galaxies, such as M84 and M86, which are, I think, the bigger lenticular galaxies there. So this image was taken on the night of May 7th, again through the Canon 60DA, using a Skywatcher Equinox 80 ED refractor, but a 400 millimeter focal length. This was a stack of 29 300-second exposures, processed in PixInsight, stacked and processed in PixInsight. All right, next one, please. So this is the EYES galaxy, which I think I had as one of the observing challenges. So this pair of galaxies there are actually part of the Markarian's chain. They were kind of down the middle of the chain there. So, you know, I was looking at them and I was wondering why are they called eyes? I guess they kind of look like eyes. I'm not sure. Next slide, please. And this is why they're called eyes. Can you start the video there, Chris? Did not play?
There we are.
There we go. This is what I call the EYES galaxies. You got a nose and a pair of eyes there. So this image was taken again on the night of May 7th. And it was taken using a ZWO ASI 2400 MC Pro through my 11-inch Celestron Edge HD. This was at 2800 millimeter focal length. And it's 16 300-second exposures stacked. All right, next one, please. This is Messier 51. So this was taken on that really nice stretch of beautiful clear nights we had at the end of April on the 28th, 29th, and 30th. So I'm sure many people are familiar with this particular object. It's a pair of interacting galaxies in Canis Venatici, some 32 million light years away. It's also called the Whirlpool Galaxy. So it's an interacting pair with a dwarf galaxy there. I forget the NGC designation for that one. I thought I'd written it down, but it seems to have disappeared on me. So well, what can you do? So this was through my 8-inch Celestron Edge HD at prime focal. At prime focus. So it was at 2032 millimeters focal length. It's 45 300 second exposures stacked and processed. And all right, my last image is next. So this is the Leo Quartet, which is cataloged as Hickson 45. Sorry, just a second here. Oops. So this particular group of galaxies is about 80 million light years away. The components of this group are NGC 3193 at the top left, 3187 at the top right, which it's pretty cool. It kind of looks like a propeller. I really like the look of that particular galaxy. NGC 3185 at the bottom right, which is that sort of double bar spiral galaxy, which is kind of cool. And lastly, in the middle is NGC 3190 / 3189. It has two designation numbers. I believe the part below the dust lane is called NGC 3189, and the portion above the dust lane is 3190. So this image was taken using a ZWO ASI 533 MC Pro. Through again the Edge HD 8-inch. It's 87 300 second exposure, so about 7 hours of exposure time. It was also taken during that stretch of clear nights in April, so it was really a productive set of nights for, I'm sure, a lot of people. But yeah, that's it for me this month.
Thanks, Oscar. Some lovely shots there. Gordon, please.
So I went out to International Astronomy Day, the event that Jim organized at the chapters in Gloucester City Centre. And because I didn't want people putting their eyeballs on my telescope this year because we were still a little too close to COVID, I dug out and blew the dust off my ZWO ASI 120 MCS, which I bought, I don't know, 5 or 6 years ago, and I've never really had any satisfactory success with it. And part of it is because when I bought it, you had to cobble together all the bits, the drivers, the software, everything to be able to get a satisfactory image. Well, ZWO has come out with a nice little suite of programs that work very well with their cameras, and so I was able to use this, and I was able to put this on the display, live viewing from the eyepiece on the display of my laptop. And so I captured this image of a very nice group of sunspots using my Nexstar 6SE with a Beta solar film filter on it. And this is region 13004. And there's actually 25 sunspots in this image, in this region. According to spaceweatherlive.com, the size is about 490 millionths of hemisphere, which means it's a surface area roughly 2.9 times the surface area of the Earth. And it's an interesting little group of sunspots because it's called a beta delta. That's its magnetic classification. And so a beta sunspot means there's positive and negative polarities with simple division between the polarities. And the delta part means there are the multiple umbras have opposite polarities within the umbras. So yeah, and it's very nice. You can see the umbra, you can see the penumbras, you can see the plage around it. And the little dots, the little dark dots to the right of this, right side of this image are called pores. And so some of them are just tiny little sunspots. And this image is actually flipped in the vertical axis because of all the optics. So I was really happy with that. And according to the same website, there were 2 solar flares from this group on International Astronomy Day. So next image, please. And so this was my setup for International Astronomy Day. I had my Nexstar 6SE in the background there. I had my MacBook Air, which ran most of the day without having to be plugged in. It only had to be plugged in late in the day after about 8 or 9 hours of driving the camera and providing almost continuous video coverage on the screen. And you can see that we're looking at the moon there. So the counterweight that was keeping the box from blowing away was courtesy of Terrace. The power was courtesy of Jim and his UPS on a generator, and the box was courtesy of Chapters. And so this was the first time I've had my gear out since pre-pandemic. So it was really nice to be able to get back doing sidewalk astronomy. And so fingers crossed that the skies are going to be good enough that we can go out to Carp tomorrow.
Good
Thanks.
stuff, Gordon. Thanks. And you mentioned Jim a number of times there. I hear a rumor that today is actually Jim Thompson's birthday. Now, I can't verify that, but if it's true, I will take this opportunity to record in the Perpetual Archive birthday congratulations to Jim. Thank you. Okay, who next?
So this is the best shot I managed to get this month of the lunar challenge, the crater Maginus. And that's right in the middle of the photograph there. There's Tycho just up and to the right, and Clavius up and to the left. And Maginus is a bit like Clavius in having a large number of smaller craters on its rim. This was taken on May the 9th, and that was about 1 day after the first quarter. Next one. I had also tried on the day previous, exactly at the first quarter moon, and I didn't even realize that I'd caught the crater until I looked again afterwards. So I've shifted the picture around so it lines up with the previous picture. And Chris, if you could just jump back and forth. And there you got the shadows. So that's the sunrise over Maginus. Both of those were taken from 5-minute videos about the best 10% of the shots stacked up in AutoStacker. Next one. And this is my best shot of the lunar eclipse. If you remember the weather that day, it was just horrendous. We had rain a lot of the day. And I was sitting around in my living room at about 9 o'clock that night thinking, am I going to see the eclipse at all? And this thunderstorm was shaking the windows. But by 9:30, it didn't seem like it was going to develop into anything. So I got out the telescope and went up to the experimental farm just in between Fisher and Merivale, and found a nice place just on the bicycle path there and set up the gear. And the clouds were still there. I could see flashes of lightning on the horizon. And then almost exactly 10:25, when the umbra was just touching the lit surface of the moon, the sky cleared. And it was perfectly clear for the next 2 hours. And then the fog came in. So next picture, this is a montage of all of the shots I managed to get from, as I say, around 10:25, when you can just see the hint of the umbra touching the moon's disk, and then through till about 12:30 or so, and then the fog came in. So it was a very interesting evening, and I had a little mini star party on the go up there, because I was joined by about maybe 15 or 20 other people at different points, moving in and out, watching it. Next one. Now, this is my other challenge object for the month. This is the umbrella galaxy, NGC 4651, the intermediate challenge. I couldn't get the easy challenge because it wasn't easy. It was right overhead, and my camera kept bumping into my tripod. So I'll have to wait for the Big Dipper to move around a little bit farther before I can get an image of that one. Next one. However, the Coma Berenices was in a very nice position the other night. This was just a few nights ago now. And so this is the Needle Galaxy, or also called Berenice's hair clip. And I've been playing around with a trial version of Noise Exterminator. So I'm still learning how to use that, but you can get a much smoother image, even if you've got a bit of noise in the original. Of course, this is from a very light polluted backyard here in Ottawa. So I did have a lot of light pollution and noise to get rid of. So I'm fairly happy with that package. I think I'll keep on trying to use it, and I'll pay for it. Okay, that's all for me. Thank you very much.
Thank you, Richard. Taras, you're next. I think you're muted, Taras.
How about now?
Okay, gotcha.
All right, so must be my headphones. So this was opposition of Jupiter and Mars on May 28th. And with this opposition, the planets were about 35 arc minutes apart. But the problem was that this was about only seen around 4:30 rather a.m. for the planets to be high enough right before the sunrise. And the problem number two were mosquitoes. So at FLO that morning, they really tried to get the best of what they could. So I had a really small period of time by running between the telescope and the mount and sprinkling myself with the DEET. So I didn't really take any too high quality pictures, even though there was a chance for, there was actually 3 planets in the sky that night. So you can see the close up a little bit of Jupiter and Mars in the upper right corner. And if you go to the next slide, you'll see them actually fit in one shot, which was shot with the DSLR camera and my 2000mm telescope with the 0.6 focal reducer, and the DSLR camera chip was able to fit them into one frame. You see the moons of Jupiter or fall of them, which was quite good surprise, and Mars as a bright blob in the lower right corner. Let's go to the next slide. So I tried to reduce the exposure for the next pictures and get some details of the planets, but because it's DSLR, it's not really the best equipment for planetary shots. So the details on Jupiter are barely seen. You can see a little bit of a hint of something darkish around like 6 o'clock, closer to the bottom of the planet, which was actually a shadow of Ganymede. And if you go to the next slide, we can see it clearly now with the different camera, which I took this picture with. So this was this time the planetary camera with RGB filters, and the shadow from the Ganymede moon, which is to the left of the planet, can be clearly seen now. And let's go to the next slide. And Mars was, as I said, about like 32, 35 arc minutes away from Jupiter. It's really small still. It's getting larger now with every week, but a few days ago, and on this picture, it was only 6 arc seconds in the diameter. And you can see it's just slightly more than a half illuminated. So it's still quite not really the best view of it yet. However, by the end of this year, around Christmas, it's going to be best time to view Mars with about like 17 arc seconds diameter in size. Let's go to the next one. And there are actually 3 planets, or even 4, Saturn and Venus that night, nicely aligned, but Venus was way behind the trees and very close to the horizon. So instead, Saturn was about 25 degrees up. And the problem was, though, that, as I mentioned, this was really short period of time before the sunrise, and the low contrast of sky when it's quite bright kind of eats up the details. And there is not really easy way of extracting those details when you don't have enough contrast in your original material. So, but this, I like this picture of Saturn because it's like its first appearances now for this season. It's going to be rising earlier and earlier, same as Jupiter as well. And that night it was about 25 degrees up. Thank you.
Excellent.
Okay, Taras, I'm sure Cassini 4 might have been happy with the shot of Saturn there. Okay, next, please.
Yeah. How do you do? This is M106. It's one of the challenge objects. Next image, please. This is the umbrella galaxy, which is another challenge object. And you can see the umbrella, and it's apparently the remnant of a galactic collision. Next image. Another challenge object from Oscar. This is the eyes. I think this is kind of neat. I like this object. I might put more time in on it, get some color. Next image. M11, not M111, 11. It's a globular cluster, I'm assuming. And the only reason I took a picture of it was I was avoiding the moon. The moon was up and bright, and I just aimed in the other part of the sky and got this, a lot more stars than I thought I was going to get. Next image, please. M12, gumball cluster. Same reason, aiming away from the moon. I got this. This is pretty. I like this cluster. Next image, please. This is one of the very first things I ever saw in my telescope. It's the Albireo pair. It's a monstrous red giant next to a blue star, and they are not actually binaries. They're apparently 60 light years apart, and they're about 430 light years from here. But they're both very, very large. One is 5 times the mass of the sun. The other is 3.5 times the size of the sun. Anyway, pretty shots. Each one is 5 seconds long. Maybe 20 pictures, 20 images to get this. Next image, please. Yeah, this is M17, the Omega Nebula, or maybe the Swan Nebula. It's apparently the brightest and most massive star forming region in our galaxy. It's in Sagittarius. As Andrea said, it's up for the summer. Get out and look at it. It looks best with small little refractors, but anything at all you point at Sagittarius, the teapot, if you want, it's fantastic. You'll see more there than the rest of the sky combined. Have a great day.
Thank you again, Bob. And now Paul.
There we go. How's my audio?
It's good, man.
Okay. I'll try to be quick because I see it's late. Anyway, good evening, everyone. I trust those who could get out to see the total eclipse did so 3 weeks ago. As you've already heard, after some clouds threatened to rob us of the opportunity, it seems that a good portion of Eastern Ontario wound up with relatively open skies for at least the first half of the event, including most of the totality phase. For the event, I had 2 cameras rolling, my Canon RP with 35mm lens and my 70D with a 300mm lens. I plan to actually have these on tracking platforms, but as Oscar has already mentioned, we had to scurry a bit to try to get ahead of some incoming clouds. So I just wound up placing them on stationary tripods. We had to shift our location. We originally had planned to be up near Calabogie, but then wound up at the lower Rideau Lake to get ahead of those clouds. This 300mm view was taken about 10 minutes after the end of totality, and as you can see, some pesky clouds had already started to find us. Next one, please. So this composite image shows several stages of the eclipse, starting at the top from about half an hour after the beginning of the partial phase, and then working around to maximum eclipse depth at the upper right corner. I took almost 1,000 images with the 2 cameras that I was running, with the thought of doing some time-lapse sequences of this event. Unfortunately, the storm event that hit our area 2 weeks ago put a dent in my available processing time, so those time lapses will need to wait for a later meeting. A personal note of interest on this eclipse: my first grandchild was born as this eclipse was happening, so I was thinking maybe I'll nickname her Luna when she's a little bit older. I was going to suggest it to her parents, but yeah, that's another story. Anyway, about 40 minutes after totality, if we can get the next one there, please, Chris. Yeah, about 40 minutes after maximum totality at our location, the clouds started to seriously move in. At that time, Oscar launched his drone to try some aerial astrophotography. And hey, Oscar, I thought you were going to show that one tonight. So as he was flying his drone overhead, you can see the clouds are already moving in there. I also caught this view of it flying right over me. And as you can see, those clouds are pretty low because parts of the trail of the drone actually above those incoming very low-hanging clouds. You can see just how low they are as they obliterated some of the light trail from his drone. So hey, Oscar, I'm looking forward to seeing that image next time.
Yeah, I'll show it
next one, please. All right, so last Tuesday morning on May 31st, the Tau Herculid meteor shower occurred that Pierre Martin talked to us about last month. This originated from debris that was shed by the breakup of comet 73P, Schwarzmann-Bachmann 3 back in 1995. According to the International Meteor Organization, the shower was at its most active between 12:15 and 1:30 a.m. our time, with a sharp maximum of 50 meteors per hour around 12:40 a.m. So it wasn't the potential meteor storm that we'd been crossing our fingers for, but certainly a tribute to the predictions of Joe Rayo, a lecturer at the Hayden Planetarium, whose data analysis indicated that a shower was possible at this time. The skies over the city of Ottawa weren't too cooperative that night, from what I gather looking at the satellite images. But fortunately, my location, about 20 kilometers west of Almont, was lucky to get a fairly clear break centered on the shower's radiant during the most active interval. However, during the hour and a half of a fairly clear sky that I had, I only observed 7 meteors, of which I believe 5 were Tau Herculids. I had 2 cameras rolling with wide-angle lenses and just mounted on tripods, so no tracking involved here. They were aimed both to the right and the left sides of the radiant, with a bit of overlap between them. The predictions for the shower were that the meteors would likely appear not very far from the radiant, and that they would not be very bright and would have relatively short trails. That is indeed what I saw and recorded, though in the 330 frames I took, only 6 meteors were captured. The exposures were all 23-second shots at ISO 3200. This view is a composite of all those 6 catches. And if you're having problem finding the 6 meteors, well, the next slide should help. Next one, there we go, thank you. The 6 are indicated here along with one bright star in the field, Arcturus. The shower's radiant is also indicated. The brightest meteor captured is at the upper left side, and the second brightest down at the bottom, just right of center. The dimmest is down near the bottom right corner, just barely visible here. The next 2 images are just zoomed in versions of this image and show the right and left-hand sides of this field to give us a closer view at these rather faint meteors. Next one, please. So this view is the left half of my field, and it shows the brightest catch of the night, which occurred at 1:08 a.m. I'm guesstimating its brightness at between magnitude +2 to +3. Next one, please. This is the right half of the field containing 4 of the 6 captures. My second brightest capture of the night is at the bottom left, and the next brightest is right near the center. And this one exhibited an interesting double flaring in its trail just before burning out. The faintest capture is the little dim guy near the middle of the right edge of the frame. Next one, please. So this is a slide of the lunar challenge object from last month, the walled plain Maginus, that Richard already showed you in his very nice high-res capture of this object. This crater-riddled circular formation is about 164 kilometers in diameter and is nestled between the well-known craters Tycho and Clavius in the moon's southern highlands. This simple view I took was just with a 300 or a 600 millimeter telephoto lens and a Canon 70D camera on a stationary tripod. Next one, please. So my last 2 slides are of last month's advanced challenge object, Carp 120, better known as NGC 4435 and 4438, and informally referred to as the EYES galaxies. They are 2 members of the Markarian's chain of galaxies in the Virgo cluster and are visible with a relatively small telescope. I took this view, excuse me, with a 300 millimeter lens at f4 and Canon 70D on an auto-guided Star Adventurer mount. It's a stack of 13 2-minute exposures at ISO 2500. We'll zoom in here to have a closer look at the eyes. So my final slide here are of the eyes there, and they're both about 52 million light years from Earth and are a pair of interacting galaxies. The smaller of the 2, NGC 4435, is a barred lenticular galaxy, and its close interaction with the larger NGC 4438 is in part responsible for the very distorted disk and tidal tails pulled out of its neighbor. However, there's also evidence that some of NGC 44's 38 very obvious distortions may be due to additional interactions between it and the larger nearby elliptical galaxy M86. Given the number of galaxies crowded into this region of space, it's quite possible that both the EYES and M86 have had numerous previous interactions in the distant past. That's it for me tonight. Hope you have a good month. Wishing you all warm weather and clear skies. Take care.
And thank you, Paul. Now to Oscar's observing challenges last month. You've seen most of these, all of these reported on. And so next slide, please, Chris. For the beginners challenge this month, we've got Messier 107, and globular cluster in Ophiuchus, 7.9 magnitude, 10-minute size, nice little target. Next one, ARP 272, trio of 3 interacting galaxies in Hercules. You can see the rest of the details there. I love ARP objects. I like Harlan ARP as a iconoclast of the 70s and into the 80s. And again, if anyone would like to do a presentation on his life and career and his influence, I think that'd be marvelous. Next, please. The Deep Sky Challenge, advanced, NGC 6692, more interacting galaxies. This appear in Lyra, and you can see the rest of the details there. Lunar Challenge, please, Chris. Mons Pico, a solitary mountain lying in the northern part of Mare Imbrium, 2,500 meters high, good sized mountain. And I'm not sure when in the lunar cycle would be best to try to acquire that. Maybe someone's got some information. So to the summary, please, Chris. There's our objects for the month of June. Next, please. Okay, we're taking back the night. First public star party for RASC Ottawa in 2022 is tomorrow, weather permitting. Usual location, the parking lot adjacent to the Carp Library and the famous or infamous Defen bunker at 3911 Carp Road. Andrea's already sent out information about this, suggesting arrival times around 9:30 or 10. Anything else you'd want to add, Andrea?
No, other than we're going to make the go, no go in the morning.
All righty.
I'm probably I'll send the email and I'll put it on the Facebook page tomorrow.
Hold on. Thank you. Next, please, Chris. So Fred Lossing Observatory back in full service. Masks are still recommended inside the clubhouse / warm room, but come one, come all, please. Next, the schedule for star parties for the rest of the year. Next one at FLO will be June 25th against a waxing crescent moon. Again, members only, but guests with members are welcome, and please, you are also encouraged to bring your own equipment. Next one. Usual information regarding the facilities provided by RASC Ottawa. Always like to emphasize the subsidized magazine subscriptions that are available through the centre through Stuart Glen. Next up, thanks to everyone involved tonight. Yes, it was a long session. I'm sorry, but I'm not sorry. When there were so many observations and so on coming in, who am I to be the arbiter? Particular thanks to our guest speaker, Nathalie, Ouellette, and all the locals for their ongoing contributions. Next,
Mick, we had a maximum at any one time of 70 people, so probably unique about 80 people tonight.
Okay, thank you for that, Chris. So the video, including presentations, observations, challenges, and our absolutely fabulous monthly newsletter, Astronotes, are all available on our fabulously well-provisioned website at ottawa.rasc.ca.
I'd like to know what a stonker is.
Stonker means absolutely bloody marvelous. Don't you people speak English? That's okay. Moving along. Okay, so next meeting will be on the second Friday of July. Obviously, this is to avoid trying to get people's attention on Canada Day. So second Friday, July 8th, usual bat time, usual bat channel. And I have to point out that the guy on the left there, Chris tells me it actually is Dave Chisholm. I don't think it is, given that he's admitted to cutting and pasting Dave's head onto someone else's photo at the podium.
I believe that's my body.
Hang on, who said that?
That was Oscar speaking, and I can
Oscar.
guarantee you that the head is Dave. I forget whose body I used, and I'm waiting for an image of you to crop into this until we can actually get back in person in the museum and take a new image.
Thank you. You've grasped my sentiment exactly. So look, everyone, thank you for attending tonight. I thought it was a lovely meeting, and please, if you are motivated to bring forward talks, presentations, songs, dances, juggling, whatever, forward them to me, meeting chair at ottawa.rasc.ca. And that includes anyone who's interested in Calvin Clatt's offer for a walk around of the Dominion Observatory sometime one weekend in July or August. And with that, I will wish you fond adieu, good night, buenas noches, dolce sueños, and we will see you next month. Thank you.